Yeah, so in this particular video, what we are going to do is we are going to study about the logic gates. So a deep insight of logic gates will be discussed in this particular video. We'll start with the AND gate and we'll go up to OR gate and AND gate, NOR, XOR, and everything. All the gates will be covered, and we'll see how these all gate function and how we can extract the output of these logic gates. So the first and foremost gate is the AND gate, and it is also known as all or nothing gate. The Boolean expression for this particular gate is y equals to a dot b. Y is the output, where a and b are the two individual inputs. The truth table we'll show in the next slide. So this is the symbol of this gate. It is just a D, a capital D. And when you apply two inputs A and B, the multiplication of both of them will be given in the output in the form of this A dot B. And as far as truth table is concerned, this is the truth table of AND gate. If A and B are the inputs, so there must be four possibilities like 0, 0, 0, 1, 1, 0, and 1, 1. And when we multiply both of them, we'll get the output. And as we know that 0 multiplication with 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. All or nothing means when all of the inputs are high, then only your output will be high. That's why it is called as all or nothing. If any one of the input is high, doesn't mean your output will be 0. Your all input must be high, then only your output will be high. That's why it is called as all or nothing gate. And you can test what is the output of an AND gate. If both of the inputs are low, you can guess what is the output. Output is definitely low. And if one of the input is low, suppose if A is low and B is high, then what should be the output? Output should be low as well. Now, if both of the inputs are high, then definitely your output will be high. And if A is high and B is low, then your output will again be low. So this is how you can understand and remember that this logic gate's output is only high when all the inputs are high. Or you can also remember all or nothing. This is called AND gate. The unique output, when all inputs are high, then we'll get the output high. The another gate is OR gate. It is called any or all gate. That means if any input is high or all of the inputs are high, then your output will be high. Output is definitely A plus B. You just add the applied inputs. So here you can see this is the symbol of this particular OR gate. And when you apply A and B as the input, you will get Y as the output of summation of both of the applied inputs. When we see the truth table, we know that if any input is high, we'll add 0 plus 1. Always result will always be 1. 1 plus 0 is 1. 1 plus 1 is always 1. So we can see that if any of the input is high, any or all, now you understand, if any of the input is high, either A or high or B or high, or both the inputs are high, any or all, then our output will be high. And you can test what is should be the output of this particular OR gate. If both the inputs are high, obviously it is high. If any of the input is low, doesn't mean if any of the input is high, output should be high. Similarly, if both the inputs are low, then only you will get the output as low. Otherwise, if any of the input is high or all of the inputs are high, then your output will be high. So the unique output here is output is low only when all inputs are low. Now the NOT gate, it gives output that is not the same as the applied input. That means if either you will apply A or B, you will always get the complement of the complement of that applied input. So Y is always equals to A bar or Y equals to A dash. If you will apply double inverting, that means once you apply two NOT gate in a series, then your output will be the same as the applied input. Suppose if A is the applied input, then in the output Y, you will get A bar. But if you will again connect another NOT gate in sequence of this particular logic gate, then you will get again A, the right. And with the help of that NOT gate, we can also design NAND gate. That is one of the universal gate. So NOT AND or inverted AND function is there. So what if I applied a NOT gate in the series of an AND gate, then you will get A dot A bar, A dot B bar. That means A bar plus B bar, or you can directly connect it as A dot B bar. So the truth table is just opposite to the AND gate, where in the AND gate, in the case of AND gate, we were getting output 1 when all the inputs are high. And instead here in the NAND gate, we are getting output 0 when all the inputs are high. So it is just opposite to the AND gate. Whatever you were getting as the output in the AND gate, you will get this reverse of that in the NAND gate, because we are using inverter ahead of that NAND gate, ahead of the AND gate. That's why it's called not AND, NAND. So you can test if both the inputs are low. Both the inputs are low. In the AND gate, it is 0. But as you have applied an inverter ahead of it, that means a bubble is there that is representing a NOT gate. So the output will be high. If any of the input is low, then your output will be high. Right? If both the inputs are high, then your output will be low. And similarly, you will get higher. So output low only when all inputs are high. And for rest of the cases, you will get high. So not or inverted or. That is called NOR, not or NOR. So here what I have done is what we have done is we have applied a NOT gate in series with the OR gate. So when you're when you will get when you will apply input A and B, what you will get y equals to A plus B complement of the applied inputs. So what OR gate will do, it will sum up the applied inputs, and what NOT gate will do, it will just put the inverter over there. So you will get just opposite the OR gate. So if OR gate, you were in the OR gate, you were getting high when any or all in the inputs were high. So you will get the opposite input of that, opposite output of that in the case of NOR gate. So if both the inputs are low only, then only you will get the high output. Otherwise, your output will be low. So I hope it is clear to you. So you can test if both the inputs are low, then only your output is high. Otherwise, in all the cases, your output is low. So output high when all the inputs are low. This is the unique output here. And now comes the exclusive OR gate. Why it is called exclusive OR gate? Because the concept of this particular gate is anything but not all. That means if any one of the input is high, it means if both the inputs are different or any of the input is high, not all should be high. Any of the input is high, then your output will be high. If all the inputs are low or all the inputs are high, then your output will be 0. So this is the symbol. This is the unique symbol. This is the exclusive OR. Along with the OR, we again have a curve here. So that is known as exclusive OR. And this is the expression A XOR B. This plus sign, encircled plus sign represent here the XORing. So always remember the truth table of this function. It is little bit different than the OR gate. In OR gate, what we were getting output high when any or all input are high. But any and all inputs are high. But in the case, any of the inputs should be high. If all of the inputs are high, then your output will be 0. If all of the inputs are low, then your output will be 0. Any one of the inputs should be high, then you will get the all output. Or you can remember if both the inputs are different, then you will get the high output, otherwise you will get low. So you can test if all the inputs are low, then obviously you will get 0. If any of the input is high, here you can see two inputs are low, one is input high, one input is high, so you will get the high output. Here you can see all three inputs are high, so obviously you will get a low output. And here you can see if two inputs are high, only one input is low, then also you will get a high output, right? So, and the inversion of this, the inverter of that XOR gate is called XNOR gate. Why it is called XNOR? Because because we have used an inverter ahead of that XOR gate. So the explanation or expression for this particular gate is previously we were having A XOR B. So complement of that is known as A XOR B. You can also represent it like this. It is also represented as Y equals to A dot encircle dot to B. So this is the expression for A XOR B. Previously, what we were getting A XOR B. The circle, the plus was encircled. Now the dot is encircled, and you can also represent it like this. This can be represented like this. So this is the symbol. Here we are getting a bubble ahead of the XOR gate. So the truth table for this particular is just opposite to the XOR. In XOR, we were getting 0, 1, 1, 0 as the output. The output was low for when all the inputs are equal. And here, the output is high when all the inputs are equal. So it is just the opposite. When inputs are different, you will get 0. When inputs are same, you will get high output. So you can test that all the inputs are low, then your output will be high. And if any of the input is high, then you will get low output because here inputs are different. Similarly, here also your inputs are different, then also you will get a low output. And if all the inputs are high, then you will get a high output. So XNOR output is high only when all the inputs are high or when all number of inputs are low. So universal gates, what are the universal gates? So universal gates are NAND and NOR. Here I have mentioned NAND only, but NAND along with NOR are the universal gates. So it is not like that only NAND is the universal gate, NOR is also a universal gate. Why NAND and NOR are called universal gates? Because they can be used in combination to create any logic function. It is not just the logic gates, it is the logical expression that you can define using NAND and NOR combinations. That means, for example, if you want to design an OR gate using the NAND gate, then what you can do? You can provide a complemented inputs here. It is A bar. If I use a single input NAND gate, then I will get an A bar. Here I will get B bar. And if A bar and B bar will be applied through a NAND gate, what you will get? You will get A bar dot B bar full complement. And when you will apply the De Morgan's law that we have studied in the previous video, you will get A plus B and double complements. And I have also told you in the NOT gate explanation that complement of complement is cancelled out. It will be just A plus B. So this is the OR gate. This is the output of a gate A plus B. But this gate can also be designed using NAND gate. Similarly, you can design any of the gate using this NAND gate. And that's why it is called a NOR gate. Oh, sorry, irreversible gates. And along not only this NAND gate, you can also use NOR gate to function to implement any of the logic gates or logical expression. Here, using inverter, you can convert gates also. So if I'll apply two NOT gate before any of the logic gate, then I can convert that logic gate as well. Suppose if I have applied two NOR gate here, two NOT gate here before the OR gate. So what is happening here? If I'll apply two NOR gate, then I can simply uh, include bubbles here. Why I can include bubbles here? Because these bubbles represent a NOT gate. So this particular concept is called bubble law. What it is called? It is called bubble law. This is called bubble law, right? And this can be replaced with a NAND gate because the function of this bubble law gate will be equivalent to NAND gate. And if you want to see how, then I will show you that if I apply two inverters before a OR gate, so it will become a bubbled OR gate. And the concept of this bubble OR, the output of this bubble OR gate will be A bar because I have applied inverter to, sorry. So it will be A bar plus B bar. Why? For example, this is A, applied input A here, and I have applied B as the input. So it will become A bar and it will become B bar here. When both of these input are applied to here, like this, these are the input applied, A bar and B bar to this OR gate, you will always get A bar plus B bar. If I am getting A bar plus B bar to this bubbled OR gate, then what can be the input here? What can be the output here? If I'll apply A and B here. So if this is an AND gate, I will get A dot B whole complement. If I'll remove this complement, if I'll apply De Morgan's law, what will happen here? It will become A bar plus B bar. So you can see this and this, both output are same. So they can be replaced with each other. Bubble NOR gate can be replaced with NAND gate and bubble NAND. For example, if I'll use bubble AND, like if I'll apply two inverters before an AND gate, so it will become a bubble AND, and this can also be represented as a NOR gate. The function will be same. The output will be same for that case. So always remember that you can use inverters to convert any gate to another gate. And these are the practical logic gates that are available in real form. So when we talk about the physical device, that how do we use such kind of logic gates in our application as a digital devices? So they are always available integrated in the form of integrated circuits. And the TTL family of ICs are known as logic gates, and where we also use CMOS or metal oxide semiconductor families of IC to design the logic gate. So whatever logic gates you use, and or not, or whatever, XOR or XNOR, they are always available in the form of ICs, and they have been made by the form of TTL. This is for logic family, TTL family. And these TTL families are always designed with the help of CMOS inverters or metal oxide semiconductor field effect transistors or transistors. So that's all for this particular video. I hope you have understood what logic gates are, how we can use logic gates, what are the Boolean expression of these individual logic gates, and what are the truth table of logic gate. I hope this will be beneficial for you. Thank you. And in the next video, we will be studying further topics related to digital logic.